Okay. And there we should be, I think. I think that ought to work. I hope. There we go. Let me just add this. And one more thing, which is I'm gonna close the window because it's a bit loud. Despite how neatly ventilated it is. There we go. There we go, there we go, there we go. That should be golden. Yep, splendid. So, hello everyone, welcome to another live stream. And today we are going to, in fact, learn. We're going to learn, we're going to explore, we're going to fancy. That's because there is something that interests me, personally, very much. It has for a while, and despite being aware of that fact for a while, despite knowing it for a fair bit, I have not, in fact, had the opportunity to develop an intuition for it, which is something I would like to do. Okay. I was so Remco's message on. Okay. All right. So, my mouse isn't working quite as well because I'm using my sober science notebook as a mousepad, and my drunk science notebook works tremendously as a mousepad. It's my sober science notebook that sucks for it. The only problem is that I'm using my drunk science notebook at the moment to do drunk science, so I can't really use that. There we go. Okay, splendid. Hi, the figure. How you doing? It is going to be slightly annoying now that I think about it, because I will need to... This is all horrendous. But well, we live, we laugh, we love, we learn. Am I right? How you doing, figure? How's your day going? There, now it's gonna work. Beautiful. And what's gonna work? Well, this is going to work. We're just going to be doing research. I just only have content on the audio right now, so I won't hear you. Well, why do I even bother? Okay, so quaternions and spatial rotation. The neat part about quaternions are just like complex numbers. You know, ordinary complex numbers, imaginary, can describe you rotation, singular. The quaternions allow you to describe that rotation with giving you the advantage of having 3 different degrees of freedom when it comes to your choice of an axis for rotation, which is very convenient because, well, in 3 dimensions you can control it over 3 axes. On a 2D plane it doesn't matter because you only have 1 axis around which you can rotate. That's it, there are no other options. In 3 dimensions it is different. And so as such, this is what we need to go through. So let's see. In 3-dimensional space, I have covered it in the past on the video already, but I have not developed a proper intuition because back then I was really rushing through it, so this time I will also be rushing through it. In 3-dimensional space, according to Euler's rotation theorem, any rotational sequence of rotations of a rigid body of a coordinate system about the fixed point is equivalent to a single rotation by a given angle theta about the fixed axis, called the Euler axis, that runs through the fixed point. The Euler axis is typically represented by a unit vector, right? E in the picture, green arrow, that makes sense. And as my head is covering it, therefore any rotation in 3 dimensions can be represented by a vector and an angle. That I was aware of, and that is very important, because if you want to rotate things without the usage of quaternions, then you need to use rotation matrices, which means that then you are not modeling it as... Hold on, let me just have a drink. There we go. If you're using rotational matrices, then you are considering rotations on each axis separately and then combining them into a single composite rotation, which results in the same thing, obviously, but the important thing is in how you model it, in my opinion, because quaternions allow you to pick an axis and an angle explicitly. Quaternions give a simple way to encode this axis angle representation using 4 real numbers, which obviously are used in tandem with the complex part. You can be used to apply calculate rotational position vectors y0 representing a point relative to origin in R3. Beautiful. Euclidean vectors such as 2, 3, 4 or ax, y, az can be written as 2ij, ijk, obviously, with, you have to remember, I times j equals minus k, if I recall correctly. Hold on. ij minus k. Look at me, I am so educated on the topic. Hi, the Panzer, how you doing? How am I doing today? I'm doing research. That's how I'm doing. Cartesian axis x, y, z, and also obey multiplication rules of fundamental quaternion units by vector quaternion. Rotation of an angle theta around the axis is defined by a unit vector. So, we have our unit vector, in which case scenario, obviously, well, I don't need to explain what the unit vector is, I guess, but the crucial difference is that instead of having it as a vector, we have it written out as a sum, whereas normally we'd have the e's to represent the bases. In this scenario, the complex values are the bases. Quaternion product using Taylor series exponential function, the extension of Euler's formula results. This is just incredible to me. Hold on, what? Polymatrices are a set of, what extension, this extension of Euler's formula just redirects a polymatrix. Okay, that makes sense, I suppose, but oh no, that's a tangent. I'm good too. What are we doing with Cartesian coordinates? Well, that's a problem, because we are we're trying to figure out how to rotate things using quaternions. SU to SO3. I don't like these groups. The first time I've seen them was in quantum chromodynamics, and I have had a bad aftertaste ever since. Do you reckon I can work my way through this entire Wikipedia page? Sure, let's try it. Quick tangent, right? In mathematical physics and mathematics, the polymatrices are a set of 2 by 2 complex matrices that are traceless, Hermitian, involutory, and unitary. Okay, so oh my lord, I do not have much experience with linear algebra practically, so whenever I see terms like these used to describe a matrix, I read what they are and I instantly forget, because I just don't use it on a daily basis enough in order for this to actually stick with me. Oh, okay, and can I ask, how are you? Not the videos, not anything else. You can ask, yes. Very much allowed to. Let me just check. Oh, you know what's funny, by the way? I am in Britain right now, and Remco alerted me to this, actually. On my Discord server, there is the Hataki's Cat Retreat. It's a channel I just simply cannot access, because I would need to confirm my age in order to access that channel. I just can't access that channel. I'm the owner of a server. I created that channel. I have moderated that channel, but I cannot access it right now, because in Britain they just don't let you unless you verify, which is so dumb. No, Greek letters. Sigma occasionally by tau and using the connection of Isaac principle. Okay, first of all, traceless. Hold on, traceless. The linear trace of a square matrix is the sum of the elements on its main diagonal. So, okay, main diagonal has to equal out to 0. Why does that matter? What does that do? Well, what that does is, if we just what does that matter, actually? Crazy laws are in the UK nowadays. Yeah, tell me about crazy law. I just find it really hilarious, because I wasn't expecting that to happen. I mean, don't worry. I still have I'm still European at the core, so I can just access my own Discord server from Europe. Who's gonna stop me? diagonals have to be not empty, very crucially. They have to equal to 0. When you have a diagonal 0 in a matrix, that means that the vector with itself is like less impactful. So, you know, identity matrix or scalar multiplications of an identity matrix very crucially rescale each one of your vector components separately. That's important. Which means that in this scenario, since they all have to equate to 0, actually, you know, I can't picture what this does intuitively. I can't develop a good intuition for it. Let me see. Oh, this just, hold on, trace, right? Yeah, don't move me to Lie algebra. Traceless. Oh, dear Lord. Dear Lord, I don't want to be learning about Lie algebra. You know it's bad when you can't. I don't know if you can see it. Hold on, but you know it's bad when you start getting the Gothic characters in there. That's how you know it's actually bad. How do you even note it down in LaTeX? Mafrag? No, just G. Mafrag? No, this Mafrag. That's really fancy. Consider me tempted. It would be technically more efficient for me right now to do research on rotation matrices, but that one is easier of a topic than this. So I'm going the more difficult first because I'm bored, to be frankly honest. I will not sit here and pretend as if I'm a better man. I'm just simply bored. So how are you? I appreciate your concern, Panzer. I really do. I do appreciate your concern, but don't worry. Hold on, I need to send a reaction image. Okay. So, dimension is a trace orthogonal if the trace is 0 to the killing form. And the citation needed. Obviously, they added the name of the killing form, just citation needed. Uh-huh. Meaningful words from these traces. Okay, all of this is going over traces, so I should do. Okay, no, I see. That's the problem. I would like to work my way through this page, but I know for a fact I'm going to get distracted with every single slight side tangent, and that's an issue. All right. I'm sorry, I'm getting distracted with caper, just absolutely breaking my heart. Let's not get distracted. Let's just read briefly through it and not think about the intuition of them yet. Hermitian matrix is square matrix that is equal to its own conjugate transpose. Okay, that one is simple actually. It's genuinely not bad. This one I've, well, watched the recent videos. Involuntary is a square matrix that has its own inverse. That is actually really close related with Hermitian. And unitary. Those three feel very related. I feel like all right. Quantum mechanics, the equation stating that kind of spin and particle electromagnetic field. They also represent the interaction state of two. Okay. Polymatrix is Hermitian, and together with the identity matrix, sometimes considered as your polymatrix, for a basis of the vector space 2 by 2 Hermitian matrix over the real numbers under addition. Oh my lord! Right, this is mathematics. I forgot. Okay, that is. I like that actually, but that is certainly. Hold on, let me open my drunk science notebook for this. Okay. Right. Remember when I said that I wouldn't get distracted with rotation matrices? Well, here we are. One, two, three, and they are in fact step by step 0, 1, 1, 0. That one is actually quite funny. 0 minus I 0, 1, 0, 0 minus 1. Okay, good. Then the interaction of the spin of a particle with an external electromagnetic field. Yeah. Polymatrix is Hermitian. Together with the identity matrix, considered as your polymatrix. Polymatrices form a basis of the vector space of 2 by 2 Hermitian matrices over real numbers under addition, meaning that 2 by 2 Hermitian matrix can be written in a unique way as a linear combination of polymatrices. I trust you on that. Hermitian matrix once again, its own conjugate transpose. Yes, that all follows. Hermitian operators represent observables called mechanics. The polymatrices span the space of observables of the complex two-dimensional Hilbert space. The concept of polywork represents the observable control span along the cave coordinate axis in the three-dimensional Hilbert space R. The polymatrices, after multiplication by I to make them anti-Hermitian, also generate transformations in the sense of Lie algebras. The matrices these form a basis of the Lie algebra. Oh! Wait, is that really what the algebra? Oh my goodness, I really should have came back to that after. I really should have came back to this after the quantum chromodynamics, because it's actually way simpler than. Yeah, yeah. The matrices these form a basis for the Lie algebra SU2, which exponentiates to the special unitary group SU2. Lie algebra. Okay, maths. It's fine. It's fine. I can crash through this polymatrices on multiplication by I to make them anti-Hermitian. Also generate transformations in the sense of Lie algebras. The formulation of the real Lie algebra, which expresses to the algebra generated by the free polymatrices is isomorphic to the Clifford algebra of R3 and the into associative algebra generated by I1, I2, I3 functions identically as isomorphic to that of quaternions. Oh, yes. Okay, now we are. The rest is money. Associative algebra. Wait, is it just associative algebra? That may not be quite as money. Commutative ring is a ring to get A together with ring homomorphism from K into the center of A. Algebraic structure of addition, multiplication, scalar multiplication. Addition, multiplication operations together give A the structure of a ring. The addition, scalar multiplication operations together give A the structure of a module. Multiplication by the addition, multiplication of a ring. Over commutative ring, geometric multiplication. Okay, that makes sense then. It's okay, so we are still money. That's good. Single expression, right. Images are involuntary ones. I already forgot what involuntary means. Alright, they're their own opposites. Yes, reversals. Squares you back. And this right here makes sense because if it was quaternions, I hope you can see my mouse, by the way. I don't know if it shows. I hope yes, you can. Okay, good. This right here makes sense because if it was quaternions, like it makes sense why it's isomorphic. Because if this was quaternions, you have minus ij. Oh wait, no, because the I is different. Dear Lord, it almost makes sense. The minus I is tripping me up a bit. Because, well, if this right here was ijk, then how do we simplify it? Well, if this is ijk, ij equals minus k, which means it's minus k times k. What is minus k times k? Well, take out the minus, we have k times k, which is a minus 1, because k squared is minus 1, which means we have minus, this is just a 1. But then why would that be equal to minus I? Oh, it's because it's anti-Hermitian now, isn't it? Wait, no, that's not the reason. That's horrendous of a reason. These ones are isomorphic because then we have effectively 4 i's, which are not commutative. You can't swap them around. That's important. Keep that in mind, which means the I is messing with me a bit. Will not lie. Because we could just consider the multiplication between them to be undefined. We can't multiply. But we can consider it also commutative, I hope. I hope. This is not easy. Well, obviously it's not. Well, okay, no. Well, alright, I was about to say, no, this on its own is easy, but I don't want to trivialize it because it's really abstract. The part that's not easy is the fact that right now I'm trying desperately to tie it to quaternions and find the isomorphism explicitly. Because, I mean, actually, this is the money shot, isn't it? If we find the intuition for the isomorphism between the quaternion algebra and polymatrices algebra, then polymatrices are there for the spin, which means that allows us to explain that in terms of quaternions. That is the golden ticket. My good lord, we could do quantum mechanics, we could do quantum spin using quaternions, which is, as kids these days would say, pretty baller, I do believe. Which would be handy in case we wanted to cover rotations or spin in the future. I don't know when we do that. Yeah, domain trace, domain dot, anti-commutation relation. Polymatrices obey the following commutation relation. So their commutator is equal to y, JKL. There's a need, but they're indexed JKL because I is already taken by imaginary. That's funny. Well, there's the epsilon here. It's an epsilon, right? A var epsilon. What is the var epsilon, though? Wait, I'm missing something. It also satisfies the anti-commutation relation, identity to identity Kronecker delta, which means if they are different, we get nothing. That's an identity. These are not commutators. Wait, what is this operation? Poisson brackets? That's okay, hold on, because this is really, really, really dumb. This is really, really, really dumb. I mean, it's not dumb. It's not dumb, but because I don't know what this operation is. Is it Clifford algebra? If that was Poisson algebra, no, Clifford algebra is different. If that was Poisson algebra, then on one hand, it doesn't make sense because I don't recall Poisson algebra being defined on matrices. Second of all, it has the same algebra. That's kind of a biggie in the video we just made. So there would be no point in switching them. But at the same time, it says satisfy the anti-commutation relations, which like, it would make sense that this tells you information about the commutator. This is anti-commutator. No, that's horrendous. Oh, that's bad. That's an anti-commutator. Oh, no. Oh, no. That's really bad. What is an anti-commutator? Of two elements. Oh, it's just genuinely a plus. Wait, one of them is AB minus BA, the other one is AB plus BA. Okay. Intuition for AB plus BA is tricky, because AB minus BA makes sense. It gives you the difference between the two. This is really difficult. I have a whole day to figure this out, it's fine. Anti-commutator intuition is, no, I mean commutator intuition is so trivial, it doesn't even bear mention, which is literally imagine them as just the counterweight you need to swap operators around. That's simple. The problem with the anti-commutator is that, well, actually, if you have an anti-commutator BA, Linear gives you B. No, there's obviously not gonna work. The interesting part about the anti-commutator is that anti-commutator is commutative. Wait, the anti-commutator is commutative. I cannot. Anti-commutators. A, B equals BA. Yeah, it has to be, because A times B plus B times A. Unless I guess the multiplication itself is not commutative. No, wait. No, still. Doesn't matter, because addition is commutative. Make it what you want about. Addition has to be commutative. Numbers are called nombres in French because I'm hungry right now. Numbers are busted sometimes. I cannot get over the fact that anti-commutation is commutative. It just breaks me up. Right. Commutator is not commutator is anti-commutative, and anti-commutator is commutative, and that is screwing with me. What is the anti-commutator? What does it actually represent? It gives you the value of one of them, and it gives you, and to it adds the value of the other one, which means anti-commutator divided by 2 would give you the midpoint between the two operations. But if you want the midpoint, hold on. Oh, this is so tricky. Height. Add them together, divide by 2, that gives you the midpoint. Height. Subtract one of them. That also should give you the midpoint. Isn't... No, because it gives you different ones. Oh, make it, you bloody idiot. So, anti-commutator AB by 2 gives you midpoint between the two values. AB plus BA commutator divided by 2. That one also gives you the midpoint. Yes. Oh, I guess you can also solve it algebraically, but then that tells us something, doesn't matter. Which means that I cannot, for the life of me, develop an intuition for the anti-commutator. Derivation of the Dirac equation. This upsets me because it also has the same notation as Poisson brackets, which is really upsetting. Yeah, no, it is the bothersome. Okay, let's for now carry on without having a good idea of what the anti-commutator is. Because basically anti-commutator will be 0 if your objects are anti-commutative, but it will be a value if they aren't anti-commutative. Crucially, if the value, if swapping the anti-commutator around doesn't do anything. If the anti-commutator is not equal to 2AB or 2BA, that means it's also non-commutative. Sometimes an example ring helps for grasping the concept of properties. Does the page list some? Well, the example ring is SU2, right? Is SU2 a ring? It should be. I hope. group. Wait, does ring imply, field implies commutative to multiplication. Ring doesn't imply that, does it? Mathematics, ring. I don't remember where a field becomes a ring. Two binary operations, addition, multiplication, except that multiplication in the ring does not need to be commutative. Okay, yeah, then I think SU2 should be a ring. Or am I thinking of algebraic structure on polymatrices, and that is not SU2? I might be thinking of no, algebraic structure has to be a ring. Jeez, yeah, if this is an algebraic structure, it has to be a ring, but still, there is a possibility that SU2 is not a ring. And SU2 refers to something different. Addition, like addition, multiplication of interest, they will similarly do addition, except the multiplication of becoming real elements will be demonstrated in non-numerical polynomials, common matrices function as power series. Yeah, so that would be a ring then. I don't know if SU2 is a ring, but the poly matrices with multiplication on them, that is the ring we're working in. And with this, oh no, SU2 has them multiplied by I, which is close enough to be honest. Okay. Back to the algebraic properties, because I do believe it still screws with me what the anti-commutator is. That is mental. Because, I mean, yeah, if it's 0, that means your objects are anti-commutative. I get that. However, if I'm not mistaken, you could also get that information from the commutator, because if commutator is doubled, yeah, exactly. If commutator is double of what you would expect to get, then that also means it's anti-commutative, which I guess anti-commutator tells you that is, yeah, no idea, no clue. Maybe the neat part of the anti-commutator is that it tells you when something is anti-commutative, and at the same time it as an operation is commutative, which makes it easier to work with. Maybe. I haven't got a clue. I have not got a clue. We'll find out together on this magnificent journey that we're on. How Remco is okay, by the way. Just out of the blue. I'm worried. User construction, I mean, he's really good, certainly. He's gonna go some, but I just hope nothing bad happened. Alright. Didn't mean to click that. Okay, there we go. Each of the Hermitian polymatrices has two eigenvalues corresponding to corresponding normalized eigenvectors R, and then we have these, which, you know what, I'm also going to drunk. I meant to say I'm also going to note down in my drunk science notebook. Yep. I would have to look up my integral AB equals minus BA in regards to swapping position. That is often anti-but it might be something else in the context though. No. The anti-commutator is commutative. Which means that, yes, if AB equals minus BA, that means anti-commutator is 0. Because anti-commutator is defined as AB plus BA. Which means that if AB equals minus BA, then you basically have minus BA plus BA, which gives you a 0. So as I mentioned, anti-commutator tells you when an operation is anti-commutative. The pickle here is in the fact that commutator also tells you that same information. Because when commutator gives you double the value you'd expect, that means the operation is anti-commutative. The only guess I could have for why anti-commutator is useful is because we're considering them as an algebra, right? We're creating these new operations to consider them as an algebra, which means that anti-commutator algebra might be nicer to work with because it is commutative. If you swap a commutator around, like sigma, let me just zoom in so that you have an easier time reading. There we go. Sigma 1, sigma 2 is equal to minus sigma 2, sigma 1. That's the property of a commutator. For an anti-commutator, however, it works the same way. So I can open up Paint, I guess. That would, because I realize I'm describing abstract mathematics and that can be really annoying to follow. Paint, where's it? Window capture, Paint. Okay, select window capture, MS Paint. You are not capturing it. Okay, it's a it's a problem. That does okay, so alright, I'm gonna do it like a normal human being then, and I'm going to draw it out in Blender because the other one just doesn't work. This poly matrices, there we go. And geez, I'm going off on a tangent. Right, and then this I want to be Blender. Simple. Right, so the idea looks like as follows. We have a commutator A, B. This tells you AB minus BA. The idea is obvious, right? If something does not commute, then, so the commutator and anti-commutator are a separate thing on itself. Yeah, so this is your commutator and this is your anti-commutator. AB plus BA. The thing that I'm struggling with here is that intuition for the anti-commutator doesn't make sense to me, because intuition for the commutator makes sense. Like that's just, you know, that's obvious, that's the commutator, that's how much you need to add in order to commute. The anti-commutator, however, doesn't seem to have a clear intuition here, because you add them together, which means that the magnitude of your multiplication on its own changes your result, which is mental. But the reason why I'm guessing this would be the case is because we're creating these wiggly brackets equals commutation. Well, the problem here, Theo, actually, is that there is another operation we just made a video on called Poisson brackets, for which the algebra is actually like this. Not AB, that would be too much, but BA, which means this is actually BA. This is actually valid. The top one referring to Poisson brackets and the bottom one referring to the anti-commutator. Which bothers me on a fundamental level. It bothers me on a fundamental level that two things with one of them which commutes, the other one which anti-commutes, have the same notation for some reason. But it's fine. It's fine. I can make it. And then he made it. Right. And so the reason why I'm guessing anti-commutator exists then, physicists putting stuff in the past. This is mathematicians. This isn't physicists. This is anti-commutator. It's like Poisson algebra, you could argue is physics more, because if I'm not mistaken, it was motivated by the Hamiltonian. But even then, it's an abstract algebra on its own. It doesn't need a relation to anything real. The reason, once again, the reason why I'm guessing anti-commutator exists is because algebra which commutes is nicer to work with. Each of the Hermitian poly matrices has two eigenvalues, and the top ones have to be normalized by 1 over square 2, obviously, because you have two values which have magnitude of 1. The bottom one does not, however, and they are opposites of each other in the sense that I can figure it out. Normalized eigenvectors. Well, I mean, I would need to compare contrast with the matrices, would I not? X, you add on this. Remco has been coaching me special relativity recently, and I do have to say, it's actually, what physicists do is actually really elegant. I also attended a lecture about a course that's way too advanced for me, so I didn't understand a single thing, but my goodness, the approach taken was so fun. Basically trying to figure out, I don't wanna get into too much, I don't know if I can. Basically trying to figure out how black holes operate with gravity, like what happens in extremely violent interactions with gravity. And the entire bit there is that you had to like really divide it into segments and tackle each segment separately via Taylor expanding of a Taylor expansion of a Taylor expansion of a Taylor expansion. It was really elegant. I'm not doing it justice describing, or rather maybe not quite elegant, maybe is not the right word. The right word here would be creative. Yes, very, very creative. It's mental what physicists can do with the information given. It's truly crazy. And they're not making just shit up, because they turn out to be correct, which you can't just do by guessing. Hi, the Jasmine. Make it attending a lecture. Insane. It was a really advanced lecture, and I honestly, not gonna lie, going into it, I knew I wouldn't understand anything. It wasn't quite as bad as I expected. I understood more than I thought I would. But that's mainly because the lecturer was really good. The guy giving the lecture was really good at teaching. I do have to say, universities actually, I think, have a lot better teachers. Well, I mean, obviously they have a lot better teachers, but what I'm saying is that also for the level, they are a lot better. Okay, oops, didn't mean to switch. Right, so we have this, and then the opposite is -1, minus I, and the last one is swapped. So very crucially, why are we going about it that way? Well, it has to be because our top matrices are, top two matrices are very clearly different, because the last one is really close to being the identity, and it is unitary. Is that the one? Well, I mean, okay, all of them are unitary, obviously. I forgot which one I mean. I don't know the terms for linear algebra because I'm self-taught, which is why I don't know the terms. I don't use linear algebra on a daily basis, unfortunately. One day. But you know what I mean. You obviously know what I mean. We all have eyes. That has to be the difference, which means that 0, 0, 1, 0, 0, that's what it would pop to -1, it would pop to -1 because this side has to be operated, which means that we have this 0 gets multiplied by a matrix, so we have this, and then 1 times 1, that gives us 1, then this right here gives us 1 times 1, 0, 0. That makes sense. That's correct. Yes, good. Is it? I feel like I'm losing my mind. I kind of measure and yes, Theo, that is correct. That is what I. If you look here, that is what I wrote in Blender. Well, I suppose you can reorganize this equation, but I mean, that's primary school level reorganizing, so that's basically what I note down in Blender. Still, the problem is that I have no idea what is the intuition for an anti-commutator, and I'm guessing that, I'm guessing the reason why it exists is because it commutes and the algebra on it is nicer. I am guessing. I guess I could just ask Replex. That's an idea. Replex. Question. Why does the commutator exist? Okay, that's not a good question. It's a mathematician. He's gonna say because why not, and that's gonna be a completely valid answer. Because it does effectively give you the... What am I missing? It gives you the same information, or at least as far as I can see, it gives you the same relevant information as an anti-commutator. Which is what confounds me. Right. I like having a microphone on me so that I can just sit wherever I like and the sound is not going to change. That's really convenient. Pauli vector is defined by this, where we have HUDs, these must be operators. Equivalent notation for the more familiar X, Y, Z, right? But this is nicer setup for special relativity. Pauli vector provides a mapping mechanism from a vector basis to a Pauli matrix basis as follows. Oh my, I am seeing special relativity into everything I look at right now. Yes, so we have a sum where we sum over all of the KLs. Yep. More formally, this defines a map from R3 to a vector space of traceless Hermitian 2x2 matrices. This map encodes structures of R3 as a normed vector space and as a Lie algebra of the cross product as its Lie bracket via functions of matrices, making the map an isomorphism of Lie algebras. This makes polymatrices intertwined from the point of view of representation theory. Another way to view polyvector as a 2x2 Hermitian measurement element. Okay. I might be short on time, so let's skip this a bit. Cross product. Cross product is given by a matrix commutator up to a factor of 2i. Oh well, that's actually comical. That is hilarious. Huh. That is absolutely comical. I like that. I like that a lot. I have no algebra. Killing form. No, I need to look into the algebras. Tangent of a tangent of a tangent of a tangent of a tangent. Eigenvalues of norm A intermediate from the tracelessness. Yeah. Follows from this. Since this can be factorized into this as standard on the algebra. It's normal, eigenvectors are very normal, sane human expression, there, because we wouldn't want anything else. I think the eigenvectors, right? Okay, now I need to trace back. Pun intended, I suppose. Trace, funny. Polyvector is defined by... It makes sense that it has two eigenvalues. Vector basis to polymatrix basis. So this allows you to map from a vector basis to a polymatrix basis. I mean, this is all really interesting because effectively what it states, pardon me, oh yeah, I suppose you can hear me fine still because my microphone is attached to me, I already forgot. I'm walking around and pondering right now. I'm pondering my orb. Okay, so okay, so map from R3 to a vector space of a traceless Hermitian 2x2 matrices. This map encodes structures of R3 as a normed vector space and as a Lie algebra. We might need to go on a tangent of what is a Lie algebra. Okay, it needs bilinearity, it needs alternating property, it needs the Jacobi identity. I'm going to guess, Jacobi is familiar, cos, correct? Will it be? I would guess the cos. You can take constant out of a cross, that's true. You can take, it doesn't matter which way you go, you can take constants. Can you take constants though out of a cross? And can you divide the cross actually like that, by division? I'm beginning to be skeptical. I could brute force it, but that feels idiotic. So instead, let's think about it, as painful as it may be. Okay, no, I need to compute the cos. Give me a second. Ah, the ASMR of rustling pieces of parchment. I'm actually right now in a cavern. What you can hear aren't cars, those are just typical cavern noises, and I am just pondering my orb, you know, just reading through different ancient pieces of parchment, just committing incantations, you know, these sort of things, normal make it stuff. Can I consider one-dimensional vector for a cross? No, minimum is 2. So we have, oh, this requires 3 vectors, that's 9, okay. AV plus BW cos U equals, I think the man is home. The man with the legend. I can sense a disturbance in the force. I suppose we'll find out. Which means AV, we can keep that. That will give us the left side, which means AVX plus BWX VY UI, geez, that's a U, UI, minus AVY plus BWY, close bracket, UX. Right. Now them separately, so that's the left side of the cross. Now the right one, which is them separately, which would be Yeah, no, that is just correct. Because you can factor it in, which means the cos is sufficient for this. We can brute force figure it out. That's good. So these are the following axioms, which is actually really calm. I like it. I like it. Making sure that we can chuck in our constants whenever we want, making sure that it of itself is not, which we all know the course has. Jacobi, which to this day I never bothered to actually look into. I don't know what it means. Group, for example, linearity expand Lie bracket using on the property shows that xy plus yx equals 0. By linearity, you expand the Lie bracket into this. And using the, so yeah, alternating, these are both the same, and since we have this, we can, that is correct actually, astute observation. Because addition is commutative. That's really quite clever. That's really quite clever. Bilinearity and the alternating property together imply anti-commutativity. Yes. And derivation property, which that one is way easier. Lie algebra of matrices. I'm like 95% that it's Remco, but if he's cooking something, clearly. What is he? He's also just casting incantations. Subalgebras, ideals, and homomorphisms. There are a lot of jokes to be made here, but I think they can all be left implied. Lie algebra homomorphism is a linear map compatible with the respective Lie brackets. Okay, we have our Lie brackets. Oh wait, hold on. Lie bracket is not required to be associative, meaning that. Ooh, that does make sense. Yes, that does make sense. Does it? I think it does. As much as terminology as in algebras, looks really as algebra linear. Can I have an example, actually? Infinite damage. Oh, it's going for matrix Lie algebras. It's fine. Tangent victims ranges space over derivatives. Smooth curves in the matrix. Lie bracket G is getting matrices. Commutated on it. Huh. No, it's fine. Oh, that's interesting. Ooh. Ooh, that is interesting. That'd be curious. Precise, gives the identity component. Converges for every matrix. Let me just get back real quick to point matrices for something. So we're talking about. Is this SU2? Are the windows still open? Why is the outside so loud? Jeez. The basis of this. Okay, I know I'm jumping in between real quick, and I'm really sorry for that, but I'm trying to understand this. However, even though SU2 and SO3 are isomorphic as Lie algebras, SU2 and SO3 are not isomorphic as Lie groups. double cover of SO3, meaning that there is a 2-to-1 group homomorphism from SU2 to SO3. See relation between the SO, sure. Isomorphic, the quaternions. Isomorphic the quaternions of unit norm via map given by, okay. Right. Interesting. Huh. Okay. Let us now identify R3 with the span of IJK. One can then verify that V is in R3 and Q is in quaternion, then there's an R, yes. Moreover, it is the same. This means that there is a 2-to-1 homomorphism from quaternions to unit norm of the 3D rotation group SO3. Because he is in quaternion Q with this and this. Map the rotation matrix. The proper sign for sign is implied once the signs are the x component of the x components are fixed. It is apparent since both Q and minus Q map to the same capital Q. Okay. Real algebra. Finally, we're not dealing with Lie algebra. Finally, we're dealing with real algebra. Set of versus quaternion whose norm is 1, also known as a unit quaternion. Okay, good term to chuck in the vocabulary, why not? It gives another way to okay, I think I'm gonna call it quits on the stream for now because I need to do a lot of pondering and it's gonna take a while. I'm gonna go quietly ponder my orb, bang my head against the wall, drink a couple of mysterious liquids, and then maybe I'll figure it out. And for now, thank you very much for watching. Have a great day. Bye.